This is the lecture that focuses on fracture. That is the final part in the stress strain curve of a solid. And of course, the course is solid state physics. So in this lecture, what we will do is that I will try my best to explain how the stress strain curves are measured by performing tensile testing. I will speak of ultimate tensile strength, FTU parameter, and explain what is a process of necking, and that will be in the focus of this lecture, basically. Try to understand what happens in necking process. And then we can understand what happens in materials when we are performing tensile testing, and especially what happens in the local picture, in the microscopic picture, or at least closer to the microscopic picture, and what happens on the microscopic picture for the stresses. Or in terms of the better terminology, like what's a true versus engineering stress. So these are the things that I will be covering in this lecture. So let's start by looking again at the stress strain curve. And now we are interested in looking at the ending regime where the material actually breaks down, so it fractures. And there's a subtlety in the terminology, and this is what I want to point to you. And the subtlety is related to the way the things are measured, and things are measured by performing tensile testing. So we are stretching a material and we are measuring the amount of strain that the material feels when we are stretching the material. And the material fractures when the stress exceeds the value that is defined to be the ultimate tensile strength FTU. And this is where we have the dotted vertical line here by the fracture, so that at the kind of highest value that we have in here somewhere, we have this ultimate tensile strength value, and when that is being exceeded, the system, like the solid, breaks down. And interestingly enough, what may happen, and that's also visible in the stress strain curve I've shown here, the slope may turn negative right before the fracture. And this process, this fact is called a necking. And this is what we will be focusing here first. And that's pretty much what we will be focusing in this lecture. And to understand the necking, we really must look into the way things are measured, so that we need to know how stress strain curve is being extracted. And how it's being extracted, characterized, is that we will perform tensile testing measurements, and that's the way we land up with these stress strain curves. And during a tensile testing experiment, what happens is that the material may taper down when we are applying stress into it. And please recall, stress was given by sigma equals F divided by A. A is the cross-section perpendicular to the applied force. And then, like the local stress may increase when the material tapers down. So tapering down means that the cross-sectional area A decreases. And that may take place and actually explains the necking process. So this is a schematic of the original tensile test. We have a piece of a material, and we start stretching the material. So we apply a tensile stress, so forces from both sides, and we stretch the material, and we see that it's being tapered down, and we see that the local cross-section here narrows down when we are stretching the material, applying a tensile stress. And because now this is tapered down here, this cross-sectional area is smaller here in the middle than nearby. So it just implies to us that the local stress, sigma local, is actually larger in the middle part of the material than in the nearby regions. And this is actually important. So material can be strained, and then we apply a smaller pulling force F, and we are still straining the material because the local stress is actually being increased. And then the measured stress and the strain can actually, in fact, in this case, actually differ quite dramatically from the real or local stress and strain. So like in this case, like when we really start seeing some kind of like a breaking down of a material happening, it really might be the case that the cross-section has been decreased to a very low value, and seemingly it seems that we are not stressing the material much, but nevertheless, like this is the regime where catastrophic breakdown happens and the material fractures. And this is the kind of force when we speak of the ultimate tensile strength force. And then subsequently, because of this fact, we have two types of stress that actually exist in the system. So there's this engineering type of a stress, which is the amount of stress that the engineer that is using the device seemingly thinks that the material is being stressed with, because the machine says that I'm inducing this amount of force into the material. And then there's this true stress, which is taking place in here in the actual material. And recall sigma equals F divided by A. When A, the cross-section becomes very small, then the true stress actually increases dramatically. And this is what explains the necking behavior in the stress strain curve. So that we don't need to physically impose that much of stress anymore on the system, because the cross-sectional area in a local location has been changed, decreased dramatically. And this is what happens in process of necking. So the material still breaks only after the local stress really exceeds the value of the ultimate tensile strength, FTU. So this really is the case. When the local stress is larger than the ultimate tensile strength, the material breaks down. But because of the material can actually dramatically taper down during the process of tensile testing, this local stress value may be surprisingly different from the seeming stress value, the engineering stress. And this is the mechanism that works out when we are trying to understand the breakdown of a ductile material, so that we have this kind of breaking process. And when we have a brittle material, the mechanism for fracture is different, and this is called brittle fracture. And this is actually quite different, and this is actually quite complicated, and thus it's beyond our scope. And this is the kind of picture that hopefully highlight what happens. So instead of when we have a brittle material, it doesn't taper down because it's not ductile. And then how it breaks down is that we then have this brittle fracture taking place. And what happens here is actually quite complicated. And here I will also spoil you some of the fun, defects will also play a role in that formation. But the treatment will not be very easy, and we cannot make any easy qualitative description of that right now. So let's just say that this is beyond the focus. At least we have understood how ductile materials break down, and then we have now understood the necking process taking place in the stress strain curve, and now we have covered all the parts of the stress strain curve. So we have essentially gone through our chapter 3, where we were focusing on the mechanical properties of lattices and solids. And now we will generalize, we will move a little bit in our description, and we will return to the crystalline nature of our solid, and we will start looking the properties based on the ideal crystalline structure. And in the next chapter, we will look into the thermal properties, and then in the chapter 5, we will look into the electronic properties. Thank you for listening, and please, I hope you enjoyed the ride. And you have enjoyed the ride so far. Thanks and bye-bye.